The fourth major concept in evolutionary biology that is really critical for understanding how to think about medical problems is adaptation. And adaptation is a concept that has been problematic and it needs special attention, but we also need to understand how do we recognize when something is an adaptation. Why is it problematic? Well, adaptation is the central character in just so stories. These are often coupled to some imaginary environment in the evolutionary past that has just precisely the characteristics needed to make a favorite hypothesis plausible. We shouldn't believe such stories. And if that is the only basis for calling something an adaptation, well, you can forget it. Claims of adaptation should therefore not be accepted unexamined. Any hypothesis of adaptation needs to be tested against alternatives. Evolutionary biologists have devoted quite a bit of thought to this, and they've developed several criteria for recognizing adaptations. So here are some of them. Natural selection itself, if you can observe it, perturbation criterion, the functional criterion, the design criterion, and the invasion resistance criterion. So we'll step through those to see what they mean. Natural selection itself. Now, natural selection on a trait, as we've seen, exists given a correlation between variation in the trait and variation in reproductive success. A response occurs when some of the variation in the trait's heritable. So, if you can document heritable changes in the trait that result from a demonstrated correlation of trait state with reproductive success, then you've pretty much nailed it. You've watched natural selection in action. And in the many cases of experimental evolution are cases in which that has been done. So in a case like that, the adaptation is the change in the trait. It's not the ground state of the trait. The adaptation is the amount of change that's occurred because of the observed selection. The second criterion is the perturbation criterion. So for that, you need both a predictive model and an experiment. The adaptation is then the state of the trait that's predicted by a model that's tested and confirmed by using some method to perturb the phenotype out of its optimal state, and to demonstrate that the fitness of the perturbed phenotype is lower than the fitness of the predicted one. This is not easy to do on humans, but it can be done with clutch-size experiments in birds. And one of the best was done by Dutch biologists working on kestrels. So here is a kestrel. And these biologists who were working in the northern part of the Netherlands manipulated clutch size and measured reproductive success. They had reduced, control, and enlarged clutches. And these are the sample sizes. The number of baby birds that were fledged coming out of the reduced clutch was 2.6 on average and nearly 6, 5.8 in the enlarged clutch. And if you ask what's the reproductive value of that clutch, in other words, how many grandchildren are going to result from having a clutch that size, well, the enlarged clutch was producing nearly 7, and the reduced clutch was producing about 3. So based on that, it would seem like it would pay kestrels to lay more eggs. However, look at what happens with the parents. The local survival of the parents with the reduced clutches is about 65%, 0.65 per year, but it's only about 43%, 0.429 per year for the enlarged clutches. As a result, the reproductive value of the parents, the number of offspring they would expect to have from that point on, including this clutch, is about 10 for the reduced clutches, and it's only about 6.7 for the enlarged clutches. So the total value, the total reproductive value of having a reduced clutch is about 1 full offspring below that of the control clutch, and the reproductive value of the enlarged clutch is about half an offspring below. What this means is that kestrels know the right number of offspring to have. That is determined by a trade-off between the number of offspring that they have and their own survival. And the result is that we can call their clutch an adaptation by the perturbation criterion. The third criterion is the functional criterion, and it defines adaptation as an appropriate plastic response. So under this definition, an adaptation is the change in a phenotype that occurs in response to a specific environmental signal, and it has a clear functional relationship to that signal that results in an improvement in growth, survival, or reproduction. Otherwise, it doesn't appear, and it doesn't appear because it's costly. So it is a change that is produced only when it pays to produce it. Here are some pretty convincing cases. Here is a water flea, Daphnia, which is the first one. Daphnia will develop spines, a longer tail spine, and it will develop a helmet on the top of its head in the presence of dissolved molecules associated with predators whose efficacy is reduced by spines and helmets. They have a reproductive cost, and they're not produced in the absence of predators. Daphnia producing spines and helmets lay fewer eggs. Here are the eggs. Bent shells in barnacles make them resistant to snail predators, but they reduce their fecundity. Same cost-benefit analysis. Snails that are parasitized by castrating digenetic trematodes, schistosomiasis, reproduce earlier. So these are all convincing cases. They are induced responses. The fourth criterion for adaptation is the design criterion. Adaptation can be recognized by its complexity and its conformity to some a priori design specification. In other words, by its resemblance to something that an engineer might design. Any complex organ that performs a difficult function efficiently can therefore be thought to be an adaptation by the design criterion. For example, the human eye, when dark adapted, can detect the arrival of photons that are produced by a single match at a distance of 10 kilometers. That is doing something efficiently with a complex organ that is a difficult task. And that is why sailors in wartime do not strike matches when they're out on board ship, because they can be seen by a submarine at a distance of 10 kilometers. Now, to judge such claims of adaptation by the design criterion, George Lauder came up with 5 questions. The first is, have any experiments done to support the claimed function? Does it really have that function? Second, has the performance of the trait in fulfilling that function been compared with alternative states? So can you actually find variation that would allow you, as with the kestrels, to look at alternatives and see what the fitness result was? Does the phylogenetic analysis suggest that the state that's claimed to be an adaptation is repeatedly associated with the kind of natural selection that's needed to produce it? Could the trait have been selected to this state as a byproduct of selection for some other trait? In other words, are you actually asking the right question? Are you really looking at the thing under selection? And then finally, is it a spandrel? And by that we mean, might the claim of adaptation be confounded by an inappropriate abstraction of just a piece of the organism from the larger whole in which it's embedded? An example of the spandrel might be the chin. The chin on a human may simply result from the fact that the human face has been reshaped by selection since our chimpanzee ancestors to be a bit more vertical, and that brings out a piece of bone that looks like a chin, functions as a chin, but it may simply be part of the reforming of the entire head. So the number of those criteria that are satisfied is a measure of how well the claim of design has been confirmed. Then the final criterion is the evolutionary stable strategy, ESS, or invasion resistance criterion. So think of a population with a trait that's a candidate for being an adaptation. To test that claim, allow the population to be systematically and repeatedly invaded by all possible alternative states of that trait in all orders and combinations. So this is the kind of thing you could do on a computer. If the candidate adaptation can resist invasion by alternative states, then we can say that it is an adaptation in the sense of being an evolutionarily stable strategy that resists invasion. Now, that's a pretty good logical criterion, and it's a pretty tough one, but it doesn't cover all cases. For example, if A beats B, beats C, beats A, then you get an eternal cycle. That is what happens in the rock, paper, scissors game. The state that resists all invaders might not be attainable in phenotype space. In other words, there might be a constraint in the system such that the resistant phenotype is not something that you can get to starting from low frequency. Another possibility is that there's negative frequency dependence, and that yields an adapted set of phenotypes rather than a single best adapted phenotype. In other words, the stable state of the population is a mixture of things rather than a single thing. Cases where the invasion challenge is hard to arrange and the ability to resist invasion have not been convincingly tested won't be covered by this criterion. It's a rather difficult criterion to fulfill. So the summary on adaptation is that when you observe natural selection, that is the best demonstration that something is an adaptation. Perturbation is also quite convincing. Function, well, in that case, the induced responses are convincing, the Daphnia helmet sort of thing. The design claim is plausible if Lauder's questions are answered, and there are some things which are so intricately and efficiently designed in biology that it's almost perverse not to claim that they're adaptations. The invasion resistance criterion is logically an extremely good one, but it's only as good as the mutations that are actually tried, and it's rather difficult to arrange experimentally. So that is the summary on a critique of adaptation. And the bottom line is that adaptation is only problematic if it's not tested or if it's not testable. One should beware of untestable claims of adaptation. And this is one of those areas of science in which one needs to develop the willingness to remain agnostic if you cannot produce good evidence. It needs special attention, but we also need to understand how do we recognize when something is an adaptation. Why is it problematic? Well, adaptation is the central character in just so stories. These are criteria for recognizing adaptations. So here are some of them. Natural selection itself, if you can observe it. Perturbation criterion, the functional criterion, the design criterion, and the invasion resistance criterion. So we'll step through, often coupled to some imaginary environment in the evolutionary past that has just precisely the characteristics needed to make a favorite hypothesis plausible. We shouldn't believe such stories. And if that is the only basis for calling something an adaptation, well, you can forget it. Claims of adaptation should therefore not be accepted unexamined. Any hypothesis of adaptation needs to be tested against alternatives. Evolutionary biologists have devoted quite a bit of thought to this, and they've developed several. The fourth major concept in evolutionary biology that is really critical for understanding how to think about medical problems is adaptation. And adaptation is a concept that has been problematic, and